Hello students, this is Dr. Ben, and here's an example problem from chapter 4 that involves both the concepts of motion and forces. So we've got this person who's moving in a vertical direction, so they're moving through the air, falling towards the ground, and then they sink into some mud and they're slowed down by the mud. And the authors of the problem ask us to find the force that the mud exerts on the person. So I believe that our strategy to solve this needs to be to consider the motion first of all, and then the forces second. But actually the motion is in two parts, because the person falls through the air and then encounters the mud, and so the acceleration of the person is different in those two parts of the problem. But we can solve it one step at a time, because the speed of the person when they hit the ground is equal to the initial speed when they slow down by the mud. So we'll need to start this problem by drawing a pictorial representation. And so there are actually 3 points of interest, and I'm going to let my red line represent the ground, and we'll define the positive y direction to be up. But the 3 points of interest are the initial point that is 5 meters above the ground, and then the ground level itself, which is where the mud starts, and then the final point that's below the ground into the mud that we're told is 1/10 of a meter. Alright, so let's label these points 1 and 2 and 3, and we'll use the variables y1, v1, and t1, y2, v2, and t2, y3, v3, and t3. And we need to remember that there are two different accelerations in this problem. So during the first part, the acceleration in the y direction is just caused by gravity, and so that points downwards. But in the second part of the problem, the acceleration is upwards, and that's caused by the mud slowing the person down. Alright, so we need to go ahead and analyze the motion in steps. My immediate goal is to find the speed of the person when they hit the mud. So we need to make a table of what we know, at least for the first part of this problem. So we know the value of y1 is equal to 5 meters, and the value of y2 is equal to 0, and the value of the acceleration in the first part of this problem is going to be negative g in the coordinate system that I picked. And my goal is to try to find the value of v sub 2. We know that v sub 1 is 0. The person starts from rest. Alright, so we need to use one of the kinematic equations. We don't know anything about time, so we don't want to use any of the equations that have time. We don't know it, we don't particularly care. So there's only one equation that doesn't have the time, and that's the one that has the squares in it. So I would write down that v2 squared is equal to v1 squared plus 2 times a1 times y2 minus y1. Alright, so we can go ahead and plug in the numbers. v1 is equal to 0, plus 2 times acceleration in the y direction, I'm going to write down as minus 10 g, times y2, which is 0, minus y1, which was 5. So we have 0 plus 2 times 10 times 5, 20 times 5 is 100. The minus signs cancel out. So v2 squared equals 100, and therefore v2 equals plus or minus 10 meters per second. And we need to take the minus answer because the velocity is down, and that is negative in the coordinate system that we picked. So now we know the velocity of the person when they hit the ground, and now we can move on to the second part of the problem and find out the acceleration. All right, so now that we found the velocity of the person when they hit the ground, that becomes the initial velocity as they travel through the mud and are slowed down. So we still want to do a motion analysis, but we want to do it between points 2 and points 3 while the person is traveling through the mud. So the velocity 3 is going to be equal to 0. In this coordinate system, y2 is equal to 0, and y3 is equal to negative 0.1 meters. We know the value of g if we need it, 10 meters per second squared. And what I want to go ahead and find is the value of the acceleration that is going to be labeled a2, and it should be a positive acceleration because the person slows down due to the mud. Alright, so again, we don't know anything about the time, so the kinematic equation that doesn't have the time may be the most useful, and so that is the one that has the velocity squared in it. So we can write down that v3 squared equals v2 squared plus 2 times a2 times y3 minus y2. Alright, and we can go ahead and plug in numbers that we know. So v3 is 0, so we have 0 squared equals negative 10 quantity squared plus 2 times a sub 2, which we're trying to find, multiplied by y3, which is negative 0.1 minus 0. Alright, move the paper up and work out this mathematics. So we have 0 equals 100 minus 2 times 0.1, which is 0.2 a2, therefore negative 100 equals negative 0.2 a2, and a2 would be equal to negative 100 over 0.2, which equals 500 meters per second squared. And that number is positive, which is good because this object slows down as it's traveling downwards, and so its acceleration is upwards. Alright, so with that done, now we can go ahead and move on to the forces part of the problem and figure out the force that the mud exerts on the person as it slows down. Alright, now that we've considered the motion part of the problem of this person falling off a ledge and sinking into the mud, now we can focus on the forces part. So let's make our table of what we know. So the acceleration that we found from the first part was 500 meters per second squared falling through the mud. The velocity at point 2 was equal to 10 meters per second. The velocity at point 3 was equal to 0. The mass of the person is 50 kilograms. And we're supposed to use the approximate value of g of 10 meters per second squared. And we want to find the force that the mud exerts on the person. So let's go ahead and draw a force diagram for this situation, and then we can analyze it using Newton's second law. So as the person is falling through the mud, there are two forces that act. So the weight force would point down, and the force that the mud exerts on the person, which is kind of like a normal force, would point upwards. The acceleration of the person is upwards as they slow, and I'm going to pick the positive direction to be up to do the forces part of the problem. So this is only a one-dimensional problem that involves the y direction. So the acceleration in the y direction will be equal to the net force divided by the mass. So from the force, so we'd like to apply Newton's second law to the situation when the person is falling through the mud. So in the vertical direction, the acceleration is the net force divided by the mass. So for our particular problem, the acceleration was upwards, and we called it A2 in the kinematics part of the problem. And then from the force diagram, the net force in the y direction would be the force that the mud exerts on the person minus the weight, and then we would divide that by the mass of the person. So I need to do a couple steps of algebra in order to solve this for the force that the mud exerts on the person. So I'll have m times A2 equals the force that the mud exerts minus the weight. And if I take the weight to the other side, I get the force that the mud exerts is equal to m times A2 plus m times g. And I could factor out that factor m and get A2 plus g. So for our particular problem, the person had a mass of 50 kilograms. We found the acceleration from the first part of the problem to be 500 meters per second squared, plus the acceleration due to gravity, which is 10 approximately. So this is 50 times 510, and so that equals 25,500 newtons. So that's the force that the mud exerts on the person, and we could round that to approximately 26,000 newtons. And just to check, I've got my units and my significant figures. And I think it's wise to pause for a second and think about why this number is so big. And it's partially because the distance over which the person stops by the mud is a very small amount. It's 0.1 meters, which is 10 centimeters. So the mud is stopping the person over a very short distance, and so therefore it has to apply a very large force in order to do that. All right, so that is an example of force in motion, where we had to do the motion part of this problem first so we could find something about the force to complete it.